This is Algebra 2 with Trig, Section 7.1. We're graphing exponential growth functions. We're looking at the exponential function, and it's in the form of y equals a b to the x. To be an exponential growth factor, the a value can't be 0, and the b value has to be a positive number other than 1. We often talk about how the a value has to be greater than 0 because we don't want it to be a negative value to be labeled as exponential growth. And the b value has to be greater than 1. To be a growth function, the a has to be greater than 0 and the b value has to be greater than 1. The growth factor is called b. When we look at the graph itself, we have this line that this graph approaches, and that line is called an asymptote. It's a line that the graph is going to curve and get closer and closer to, but at no point is it ever going to touch that. And that line right now is the x-axis, where y equals 0. When you look at this equation, we see y equals 2 to the x. What that shows is that when we're here at a half, we times it by 2 to come up to 1, and we take 1 and we multiply it by 2. We're up here at a height of 2, and we multiply 2 by 2 and we get up to a height of 4, and then that become 8 and then 16. It's multiplying itself by 2 every time. It's called exponential growth. From working from the left side to the right, you can see that the graph increases exponentially. The graph passes through the point 0a. Whatever the a value is going to be this location here. So 0a. Right now it's 1 because the value in front of your b is not labeled, so that's considered a 1. And it also goes through 1 comma b. When you put a 1 into your equation, you're going to get whatever your base is. So at 1, we're up at a height of 2. So it'll always cross where that b spot is also. The asymptote in this case is the x-axis, which is y equals 0. The domain, what are the x values that you can plug into as an exponent? You can plug in positives, you can plug in negatives, you can plug in 0, so it's considered all real numbers. And another notation we can use is to say negative infinity to positive infinity. The range is your y values. What are your y values that your graph is? Is your graph down here in the negative area? No, so it's all the y values greater than 0. The interval notation for that would be 0, comma, the lowest point is 0, the highest goes up to infinity. The first portion is always the lowest point, and the second part of the interval notation is always the farthest or the highest. In this case, it does not actually touch 0, so we use a curve to represent that. If it was to touch it, then we'd use a square bracket. Infinity, it can never reach infinity. There's always another number. Infinity is a concept that it heads towards, but it never really reaches. So that's why that's curved also. An asymptote, as we've talked about, is a line that the graph approaches but does not cross. There's actually a few situations in the future that we'll see the asymptote the horizontal asymptote get crossed, but it always approaches it from at least the other side. So an asymptote is really the concept at the end behaviors more than what might happen there in the middle. But for all of these examples, it will always approach it. X approaches negative infinity when the function is doing what? As x goes to the left, the function is approaching 0. When the function moves to the right, where's the function going? The function's going up. So it's going towards positive infinity. We're going to look at the graph, and we're going to graph the equation y equals 5 to the x power. This would be considered a parent function just the way it is. You can't get any more basic than 5 to the x. 2 to the x is just a different equation. It's still exponential, but that would be a parent function also. So this is just b to the x power. The b just happens to be a 5. So we're going to plug in some numbers. The reason I picked those numbers is any other values, it would definitely fall off the graph. -1 for an exponent is going to, the negative affects the 5 by flipping it over. So now we have 1/5. The 1 says that you're going to raise it to the power of 1. So 5 to the first power is just 1. So it's 1/5. Anything to the 0 power is 1, and anything to the first power is itself. So we can come over here to our graph. And you'll see that at -1, we're at 1/5. But at 0, we're up at 1. And at 1, we're up at 5. So if we were to graph all the other points along it also, we would follow in that pattern, where this would be a line that is called y equals 0, which is our asymptote. You see that it's crossing at 0a and then also at 1b. This is the equation y equals 5 to the x power. The domain, what are the x values that you could plug into an exponential? It's always going to be all real numbers. Interval notation, we say from negative infinity to positive infinity. The range, since this doesn't have a translation, we would say that its y is greater than 0. You see that it's pretty much touching the x-axis, but not quite, and it's always going up after that. So we would say 0 to positive infinity. The end behavior. Another way you'll see end behavior written, I often like to write it with x first, but sometimes you'll see it written as f of x. So f of x approaches 0 as x approaches, and that's heading to the left. The functions are getting to 0 when x is heading to the left, so that would be negative infinity. The function approaches positive infinity as x approaches, the function goes up as x moves to the right. So that would be positive infinity. You may put a plus sign for positive infinity, or you can just leave it as infinity. On the second page, we're looking at the different types of transformations. So there is a vertical stretch that you have y equals a times b to the x. If a is less than 1, so if a is a fraction with a numerator smaller than the denominator, then we would have a shrink. If the a value is greater than 1, or as long as the numerator is greater than the denominator, we would have a stretch. So when we talk about stretching or shrinking, it's looking at the a value, specifically the absolute value of a. So we could put absolute value bars around that, because specifically we'd just be looking at what is the number itself, not if it's positive or negative. So we're going to look at this graph. The a value is 1/3, so it's going to be a shrink. The parent function is 3 to the x, so we're going to use the numbers -2, -1, 0, and 1. I'm going to change that up actually. Sorry. we're going to go the other route. We'll say -1, 0, 1, and 2. And I'll show you why. This is going to give us 1/3 because 3 to the -1 power, the -1 flips the number to the denominator. Anything to the 0 power is 1. Anything to the first power is itself. And then 3 squared is 9. I thought graphing 9 was a little bit easier than graphing 1/9. There won't be much difference on my dot placement for 1/3 and 1/9. So there's a big difference here between 3 and 9. So I'll draw my graph. I'll plot my parent function. -1, I'm up 1/3. At 0, I'm up 1. At 1, I'm up 3. And at 2, I'm up 9. Okay, so that's my equation. And I would have y equals 3 to the x. Now with that being shown, I'm also going to take all of those y values and it's going to be a shrink by a scale factor of 1/3. That means I'm going to multiply all the y values by 1/3. Instead of going up 9, I'm just going to go up 3. Instead of going up 3, I'm going to go up 1. Instead of going up 1, I'm going to go up 1/3. Instead of going up 1/3, I'm going to go up 1/9. If you thought about what 3 would do, 3 to the 3rd would go all the way up to 27. So 1/3 of that would be 9. So it almost looks like a translation. So we would have a asymptote still at y equals 0, and our equation would be y equals 1/3 times 3 to the x power. The asymptote is y equals 0. The domain is all real numbers. That would be -infinity to +infinity for interval notation. The range would be y is greater than 0. It doesn't touch the 0 line, but it approaches it. So our interval notation would be 0 to +infinity. The end behaviors. What's happening when x heads to the left? Goes to -infinity. The function approaches 0. It gets closer and closer to the asymptote. What happens as x approaches +infinity? The function, as we move to the right, the function goes up. So it also goes to +infinity. Here we have another equation. Notice we're going to use just the parent function for the table. 7/2 could be considered the same thing as 3.5. So it might be easier to think about 7/2 when we talk about negative exponents. So -1, I'm not sure what 3.5 is to the -1, but when I take -1 to this fraction, I know I'm going to get 2/7. Any number raised to the 0 is 1, and any number to the first power is itself. So at -1, I'm at 2/7, which is even less than 1/2. Then I'm at 1, then I'm at 3.5. Okay, so that's the equation y equals 7/2 to the x power. You should have that in parentheses. And then the negative tells you that there's a reflection. Over the x-axis. So that means we're going to multiply all the y values by a negative. And then we would draw in our line. That gives us an asymptote here at y equals 0. And our equation is y equals negative 7/2 to the x power. The asymptote, again, is y equals 0. The domain, what x values can you plug in? All real numbers. That's negative infinity to positive infinity. The range, if you look carefully, notice that the red graph goes down. So it's going to be less than 0, which would mean the smallest value would be negative infinity, and the highest value would be 0. So that would be how you would write the interval notation. As x approaches negative infinity, the function is approaching 0. As x moves to the left, the function is going up towards 0. As x approaches positive infinity, the function, notice that when we go to the right, the function is going down, is going to negative infinity. This equation here, the parent function, that's exponential. That's exponential growth. But when we do the reflection, remember we talked about earlier that the a value has to be positive for exponential growth. In this case, it's negative. So this red graph is not an example of exponential growth. It's exponential. It's multiplying itself repeatedly. 7/2, 7/2, 7/2, 7/2. So that exponential concept's still there, but it's not considered growth. And it's not considered decay either. Another type of transformation we can do is called a translation. So we're going to take our equation y equals a times b x minus h plus k. That is a horizontal translation. It's going to horizontally translate by h units, and it's going to vertically translate by k units. It's following all the same h and k rules that we've talked about in the past. So our parent function for this is going to be y equals 3 to the x. So we'll use some numbers like -1, 0, 1, and we can even make this a little bit bigger if we wish to be 2. So what happens with a negative exponent? It flips the 3 into the denominator. Anything to the 0 power is 1. Anything to the first power is itself. And then squared is 3 times 3. So those are the values that make up the table for the parent function. You can only make a table for the parent function. The transformation that's happening to this is a translation, where the h value is 2 and the k value is -1. So that's 2 units to the right and that's 1 unit down. So we put in our xy axis. At -1 we're at 1/3. At 0 we're at 1. At 1 we're at 3. At 2 we're at 9. So that's our equation of y equals 3 to the x. And then if we're supposed to take this graph and move 2 units to the right and 1 unit down, 2 units to the right and 1 down. That means that the asymptote is also going to move down 1. So we have this asymptote at y equals -1. So the graph is going to approach that and then curve up to the rest. So we get y equals 3x minus 2 minus 1. Notice how it's minus 2. It looks like the graph might go to the left because it's minus. But the graph actually is the h value is a positive 2. The horizontal asymptote, we said, was y equals -1. The domain is still all real numbers, so that's -infinity to +infinity. The range, what is the range of our graph? Our lowest point is -1, and then it curves up. Those are the y values. So the y value is greater than -1. In terms of our interval notation, that would be -1 to infinity. The end behavior, as x approaches -infinity, the function does what? As x moves to the left, the function goes towards -1. As the function moves to the right, the function goes up, goes to positive infinity. Our parent function here is going to be y equals 4 to the x. We'll use the numbers -1, 0, and 1. -1 means we do the reciprocal. 0 is going to be 1. 1 is going to be 4. We have a reflection over the x-axis. We have a stretch by a scale factor of 3, and we have a translation, h equals 1 and k equals -2. The horizontal movement's going to be 1 and the vertical movement's going to be -2. In the past with graphs, we have made a table. And I've shown the progression of how these different transformations affect it. We can also do that directly onto the graph. At -1, we're at a fourth. 1 and 4. So that's our equation of y equals 4 to the x power. Then we're going to take that graph and we're going to reflect it over the x-axis. So we have all of our points that are below the x-axis now. And that's going to be the line y equals -4 to the x power. Then we're going to take all of those points and stretch them by a multiple of 3. So instead of going down 1/4, we're now going to go down 3/4. Instead of going down 1, we're going to go down 3. And instead of going down 4, we're going to go down 12. So you can still see that it's approaching the x-axis, but it does it a little later in the curve. So this equation is called y equals -3 times 4 to the x. Then we have our final graph, which is taking all of those points and moving 1 to the right and 2 down. There's not a big difference. These graphs are kind of landing right on top of each other. But you're going to notice and see that went down 1, or over 1 and down 2. This one went over 1 and down 2. This one went over 1 and down 2. So that's going to be the line y equals -3 times 4 x minus 1 minus 2. Went down 2, sorry. If it went down 2, then we should have an asymptote right here at -2, so our graph should actually approach that line. So we have our asymptote here at y equals -2. Our domain, what numbers we can plug in, is all real numbers from -infinity to +infinity. Our range is from, it's lower than -2. That's always your k value. As x approaches -infinity, the function is approaching -2. As x moves to the right, the function is going down. Okay, on the next page, we're looking at exponential growth models. We have this equation, y equals a times our b value here, which is our growth model, 1 plus r. So it's 100% plus your rate. A quantity increasing by a fixed percent each year, we would use this equation, where y is the quantity after t time. Typically it's a year. A is the amount that we're starting with. Whatever the topic is. The percent, the R value, is the percent of increase. Since this is growth, we know it's going to be increase compared to decrease. But we're going to write that percentage as a decimal. A lot of people have troubles remembering to switch that over to a decimal. And T, of course, is your number of time periods. So our example, in 1970, the population of Kern County, California was about 330,000 people. From 1970 to 2000, the county's population grew at an average rate of 2.4%. So we're going to write an equation using our new formula, where A is the amount that we start with, which is 330,000. We have 100% of that, plus we have 2.4% more, so that's 0.024 in addition to that. So we can put that 1 and the 0.024 together. So y equals 330,000, 1.024 to the t power. So that is our growth model. Now, about how many people lived in Kern County in 1990? Well, if you take 1990 and we look at how many years that was from the beginning of our 330,000, we find out that that's 20 years. So we can take our 330,000 at the growth model of 1.024 for 20 years. And if you type that into your graphing calculator, or into your calculator, you'll get 530,290, and those are people. Now we could do that with a graph. That would be fine. We see that this is exponential growth because the b value is greater than 1. So it would actually be way up here, and it would begin to curve, and we would look out here for what our x value was of 20 and would come up to find out where 20 was, and that would be x is 20 and the y value would be about 530,000. It's not really drawn to scale, but that's what it would look like. And of course we wouldn't take it that way too far, because that would be in terms of negative time. Here's an exponential growth function. We have something, 650 of them. It's growing at a 22% rate. What number here is considered the initial amount? 650. Which here is considered the growth factor? It's growing at 1.22. And what is the percent of increase? It's growing at 22%. The 0.22 tells us that moving the decimal twice to the right gives us 22%. That's how much it's growing every time. Alright, one more page to go. This is a lot of information. This is called compound interest. This can be a bit tricky. Compound interest. We still have A, which is amount, and we have P, which is the amount that we're starting with. We'll call it the initial amount. In problems, they often call it what is the principal. We have R, which is standing for our annual interest rate. N, this is the tricky part, N is the number of times per year the interest is compounded. We need to talk about what compounding means. And T is going to stand for the number of years. Compound interest. Each year, perhaps, like we'll look down here, each year we get 3.6%. That's added to the amount that we have. So if we start with 5,500, so if we use our old equation, A equals P1 plus R, that would be once a year. And if we're going to do this for 3 years, then we could see how much we would get if it was compounded once. That means if we were given the money at one point, probably at the end of our year, or in this case 3 years, we would be up to $6,115. Now, typically banks don't work that way. Banks are going to give you money more than just once a year. They might give you that same 3.6%. Unfortunately, it's not each time. But they take that 3.6% and they break it into amounts. So if we take our formula, 1 plus r over n, nt, this is compound interest. This was not an example right here of compound interest. This was just getting it at the end of a year. This is our compound interest. So what is the amount if our principal is $5,500? 1 plus 0.036 divided by 4. 4 is quarterly. How many quarters are there in a year? There's 4 quarters in a year. So this is 4 for your n times 3 years. That's 5,500. When you divide 0.036 by 4, you're going to get 009. So now when we add it to the 1, we get 1.009 raised to the 12th power. What this is saying is that at the end of every month, actually every 3 months, at the end of every 3 months, because there's 3 months in each quarter of a year, at the end of every 3 months, they're going to give you some extra money into your account. So after 3 months, they calculate what this 0.009 is, and they add it to your account. And then they do that 12 different times for you to figure out what 3 years is worth. And the amount that you would have at the end here is $6,124.30. Notice how that is greater than $6,115. It went up. The amount stayed the same in the beginning. The interest rate stayed the same, but how they compounded it was different. They gave you money every 3 months. So after 3 months, they calculated again, and you had more than 5,500 in it. And then 3 months later, they calculated again, which was more than 5,500. And they keep growing on top of it. Where this calculation here would have been just giving you the 3.6% after 1 year, and then again after a second year. Once a year, this is giving it. This is giving it to you every 3 months. Not the full 3.6%. Just a portion of it. Now, if you compound it monthly, if we take our 5,500, and we take our 1 plus 0.036 and we break it into 12 equal amounts, that means they're going to give it to us more than 4 times. They're going to calculate our new account 12 different times during the year. So that's going to give us, with your calculator, you can see that that would be 0.003, and that would be a 36. So that's really 1.003. So now there's 36 months in the 3-year period. Each month they're giving you a little bit of your 3.6%. So they're giving you money sooner during your total amount, so your sum is going to increase. Now, granted, it's not increasing by a ton, but here we were at 15 and now we're at 24, and at this point, if we compound it monthly, we're now at 26. $6,126 with some change left over. So the more times they compound it, the more money that we're actually making. The interest rate is the same all the time. What we're starting with is the same. It's just changing how often they give us money. Daily. 5,500 1 plus 0.036, because that's our interest rate. How many days are there in a year? 365. So we're going to say 365 times 3 years. So when we do the math here, we get 5,500. Now if we take this 0.036 and break it into 365 teeny pieces, that's a pretty small amount. 0.000098. But we're going to do that 1,095 times during this 3-year period. And again, as you might expect, the amount in the account is going to grow again. Not dramatically, but it definitely increases. You compounded it more often. Every day, you got a little bit more put into your account. At the end of 1 year, it's still a percentage of 0.036. But every time they added a little bit into your account, they calculated it off of a larger amount. And then the third day, the account was a little bit larger because of yesterday. Look down here. That compounded annually means that they're going to do it once. That formula I showed you in the beginning was A equals P 1 plus R to the exponent. Compounded semi-annually means they're going to do it twice. That means your end value is 2. And that's when we need to use this formula if it's compounded. This is annually compounded once, so really would be dividing by 1. Compounded twice. If it's quarterly, it's 4 times. Monthly, 12 times. Compounded daily. In the future, we're going to talk about compounding continuously. But that's for a different lesson.